Time doesn't move the same for everything, and sometimes it bends, slows, skips, or hides in ways we barely notice. From caves and frozen seeds to signals from space and clocks that tick differently on a staircase, the world is full of real stories where time itself seems to slip. These are not myths or theories, they're moments when time proved it can twist the rules we take for granted. The day Samoa skipped, they say not every day in history truly happened. For the people of Samoa, one day in 2011 simply never came. December 30th was meant to dawn like any other summer morning in the Pacific, but it didn't. The sun still rose over the palms, the waves still touched the reef, yet the calendar skipped straight from Thursday, December the 29th to Saturday, December 31st. Friday vanished completely. Samoa decided to move through time, literally. The island nation sits close to the international date line, that invisible boundary where one day ends and another begins. For more than a century, Samoa's position on that line had been a point of debate. Time, after all, isn't a law of nature. It's a line drawn by people trying to keep order in the chaos of rotation and trade. Before 2011, Samoa lived nearly a full day behind its biggest trading partners, Australia, New Zealand, and much of Asia. When the markets opened in Sydney on Monday morning, Samoa was still stuck in Sunday. Business calls missed, shipments delayed, families on opposite sides of the Pacific living out of sync. The difference of a single day was costing money, time, and connection, so the government decided to change it. On May 9, 2011, the Prime Minister announced that Samoa would shift west of the international dateline to match the work week of its partners. The price of that decision would be one day, a clean cut. The plan was simple, at least on paper. At midnight on December 29th, the clocks would jump ahead 24 hours. December 30th would never exist. That night in the capital Apia, church bells rang and crowds gathered by the waterfront. Children waved small flags as the countdown began, not to a new year, but to a new time. At 11:59 p.m, the second hand climbed toward midnight, and when it arrived, the next moment was already the next day. The date read December 31st. People laughed, cheered, kissed and prayed. Some said they felt strange, as if they had been pushed forward by an unseen hand. Others shrugged. It was just another night. Shops reopened Saturday morning as usual, calendars flipped ahead, and a country woke to find it had leapt one full day into the future. For the rest of the world, December 30th carried on. Planes landed in Los Angeles, clocks ticked in London, people in Tokyo went to work. But in Samoa, there was nothing to record. No birth stamped with that date, no weddings, no receipts, no sunrise listed as Friday, December 30th, 2011. It was an officially missing day. Some older Samoans remembered when the opposite had happened. Back in 1892, the islands had moved east of the dateline to align with the United States. That switch had added an extra day instead of removing one. To celebrate, residents had lived through July 4th twice, a 2-day independence celebration. Nearly 120 years later, they were doing the reverse, erasing a day to realign with a different world. For local businesses, it was a practical move. For the tourism board, it was a chance to tell a story, Samoa, the country that time jumped. For churches, it was a moment of reflection. Pastors reminded their congregations that time belongs to God, and that losing a day was still a gift if it brought the nation closer to prosperity. Some workers quietly celebrated the shortest week of their lives. Friday's wages were paid even though no one had to show up. School children joked that their homework for December 30th had been permanently cancelled. On the western tip of the island of Savaii sits the village of Falealupo, once famous as the last place on Earth to see the sunset each day. When the time shift took effect, that honour vanished. Overnight, the village became one of the first to greet the dawn instead. For locals, it was as if the world had flipped upside down. There were small side effects too. Computer systems had to be reprogrammed, flight schedules rewritten, international call centres updated. A few travellers missed connections because their tickets still showed a date that no longer existed. But in a world of digital timekeeping, the transition was smoother than many expected. What happened in Samoa wasn't a scientific experiment or a cosmic glitch. It was a reminder that time, as humans measure it, is flexible. Entire days can vanish or appear with the stroke of a pen. Standing on the beach that morning, you could look east toward American Samoa, just 100 kilometers away, and see a different day across the sea. When Samoa was welcoming Saturday, its neighbour was still living in Friday. Boats could cross the channel and literally move from one date to another in less than an hour. To the outside observer, it looked like a trick of geography. To Samoans, it felt like a small act of freedom, a choice to decide which tomorrow they wanted to live in. And so, on the edge of the Pacific, an entire nation proved that even in the age of atomic clocks and satellite time, the map of the world's hours still bends to human hands. December 30th, 2011 was gone forever. Yet for Samoa, life went on, right on time. Magellan's lost day. In 1522, when the last survivors of Magellan's fleet sailed into port in Spain, their logbooks told a curious story. Their calendar lagged. Their dates were behind. They had lost a day somewhere on the route. Antonio Pigafetta was aboard the voyage as chronicler. He recorded many details: storms, islands, crew sickness, navigational fixes. Among those notes lies a puzzle, a discrepancy in dates compared to the local civil records of ports visited. By the time they returned, their log showed a day behind the official calendar for the place they landed. The voyage began in September 1519 from Seville under the Spanish crown, with 5 ships and nearly 250 souls. As they progressed, across the Atlantic, down the coast of South America, through the strait at the tip, they faced mutiny, storms, starvation, shipwrecks, and death. Many never survived. Only one ship, the Victoria, made it home under command of Juan Sebastian Elcano. The rest had perished along the way. Pigafetta's account remains the most detailed surviving narrative of the expedition. He wrote of daily life, of scurvy, of encounters with islands, and of celestial observations. Interwoven through these pages is the unspoken shadow of a day missing. Let's trace it chronologically. In May 1521, after rounding South America, the fleet entered the Pacific. They sailed across months of open ocean, islands unknown, provisions dwindling. They made landfalls in Guam and the Philippines. In April 1521, Magellan died in the Battle of Mactan, and leadership struggles threatened the continuation of the mission. Afterward, under new captains, the voyage pressed westward through the East Indies. They reached the Spice Islands, the Moluccas. At that point, it was believed they had completed half the globe's circumference. But when they turned west toward Europe, something odd unfolded. When Victoria attempted to cross the Indian Ocean, round the Cape of Good Hope and sail north towards Spain, they expected to arrive with a precise calendar. But upon docking in Lisbon or Sanlúcar de Barrameda, depending on port, the local date was one day ahead of their own logs. They believed it was September 8th, 1522, but local records, port registers and public calendars said September 9th. So where did that day go? There was no official day-skipped order, no deliberate holiday, no emperor's edict. Instead, it seems to be an effect of circumnavigation without a dateline concept. The crew had sailed continually westward, chasing the sun. From their perspective, each new sunrise was one more day, and they counted as usual. But in moving around the globe, they effectively gained an extra sun that their reckoning didn't cancel. Pigafetta himself hinted at this as a marvel of navigation. According to early histories of the dateline, Pigafetta was among the first to note that somewhere during such a voyage, a whole calendar day must shift. He never quite said, "I lost Friday," but he recorded, "We found ourselves one day behind the people of that place in the calendar." Later historians interpreted this as the first real anecdotal evidence of what would later become the international date line. Though the idea of a line dividing days was not formalized until centuries later, the Magellan circumnavigation foreshadowed it. Some port registers, municipal chronicles and royal dispatches lent corroboration. The port of Seville, when receiving Victoria, recorded the arrival on a date one day later than the members perceived. The province updated logs, taxes and official ceremonies on that date. The discrepancy could not be ignored. It was not universally chronicled in every source, and some modern scholars debate the precise documentation. But the law has persisted. These early circumnavigators lost a day simply by sailing around the world. Without realizing the date structure must adjust, they ended behind. Imagine the moment. Victoria rounding Spanish shores, sails lowered, cannon fire echoing over the harbour, the crew stepping ashore, checking their log's calendar. Their days said September 8th, but the town hall, the cathedral bells and local courtyards read September 9th. Confusion would ripple through port officials, priests and observers. Mathematicians and philosophers later used this as proof that Earth is round and that time is tied to the planet's rotation. Some argue the logs are dusty evidence of how early navigation was wrestling with the intangible, time itself. In cities like Valladolid, Madrid, Seville, scribes recorded when the Victoria docked, when papers were submitted, when reports arrived at the royal court. Their dates aligned with the local system. Those systems never anticipated a ship that circled the globe would arrive earlier in counting than the local time itself. Navigators of later centuries would formalize a remedy, introduce a date boundary where passing from west to east or east to west adjusts the counted day. But in 1522 no such boundary existed. The Magellan expedition predated that formalism. Thus, a curious footnote in world history, these sailors completed the first circumnavigation and inadvertently demonstrated a hidden rule of calendars. In their struggle with storms, starvation and empire, they also discovered the need for a world line in time. Their logs show a day missing, not because of magic or gods, but because the world turned under them and their counting did not catch up. Flying atomic clocks, picture 4 ultra-precise atomic clocks crammed into airline seats circling the globe. In October 1971, physicist Joseph Haefel and astronomer Richard Keating sent cesium beam clocks aboard commercial jets, once eastward, once westward, and later compared them with identical clocks left behind on Earth. What they found would put Einstein's ideas of time directly to the test. These were not ordinary clocks, they were atomic clocks, using cesium beams to count oscillations with extreme accuracy. Their tick is so steady that in a single day they drift by less than a billionth of a second. Such precision allowed scientists to detect the tiniest variations predicted by relativity. On October 4th, the first flight began, heading east. The clocks flew over Europe, Asia, across the Pacific, then back via the Americas. After about 65.4 hours total, the craft landed. A few days later, in October 13th, the westward flight departed, taking roughly 80.3 hours complete. In both journeys, portions of the time were spent in actual flight, about 41.2 hours eastward, 48.6 hours westward. By the time each flight finished, the travelling clocks did not agree with their counterparts left on the ground. The eastbound clocks lagged behind by about 59 nanoseconds. The westbound ones ran ahead by 273 nanoseconds. That's a few billionths of a second, smaller than a blink. The numbers matched the predictions derived from relativity almost exactly. How did relativity forecast this? 2 factors were at play, one from Einstein's special relativity, the other from general relativity. Special relativity tells us that when a clock moves relative to an observer, that moving clock will tick more slowly, a phenomenon called time dilation. In the eastward flight, the airplane's velocity added to Earth's rotation, making the clock move faster relative to the Earth's centre. That meant its time should slow relative to a stationary ground clock. General relativity adds a counterpoint, gravitational time dilation. A clock higher above Earth's surface, in lower gravitational potential, will run faster than one on the ground. At cruising altitude, the flying clocks experience slightly weaker gravity, which makes time run a little faster. In the eastward journey, the special relativity slowdown dominated over the gravitational speed-up, so, net effect, the airborne clocks lost time relative to Earth. In the westward journey, the velocity difference was reversed, so the gravitational gain outweighed the speed loss, and the clocks ended ahead of their ground twins. Scientists predicted that for the eastward trip the net difference would be around 23 nanoseconds, and for the westward, plus 275 plus 21 nanoseconds. What Haefel and Keating measured was 59 plus 10 and plus 273 plus 7 nanoseconds, respectively. The match was startlingly close. To conceive of these differences is to imagine time itself bending under motion and gravity. Imagine you're racing the Earth's rotation eastward, time slows for you. Or you drift westward against the rotation, time gains. These are not metaphors, but real shifts measured in clocks. The experiment also resolved an old puzzle sometimes called the clock paradox, or a version of the twin paradox. If you send one twin flying around the world fast and return him, who is younger? The Haefel-Keating experiment showed that real macroscopic clocks respond just as relativity says. Time is not absolute. The infrastructure around the experiment was as delicate as the principle it tested. The clocks needed shielding from magnetic fields, temperature shifts, vibration. Each flight path was logged carefully. The ground reference clocks at the US Naval Observatory kept time to the highest standard. After flights ended, the airborne and ground clocks were reunited and compared in controlled conditions. Even the uncertainty mattered. The error bars of the measurement were small, tight, brave for 1971 technology. The agreement between predicted and observed differences bolstered confidence in relativity, not just in theory but in practice. The results ripple to this day. GPS satellites which orbit Earth run on clocks that experience both velocity and gravitational effects. Their onboard time is corrected constantly relative to ground time, so positioning on Earth remains accurate. The Haffel-Keating experiment was one of the proofs that physical time is sensitive to motion and gravity, affecting real systems we rely on. This was not science fiction. It was a practical flight test, across thousands of kilometers, with clocks as passengers. The experiment showed that time is not a universal stream but a fabric woven by speed and gravity. In 1971, flying clocks proved that to us. Cave without clocks, Michel Siffre. He entered the dark without time, no sun, no clocks, no cues from the world above, just whispering stone, silence, and the slow drip of water. In 1962, the French speleologist Michel Siffre slipped into a cave in the Alps with a radical aim: to live completely isolated from all markers of time. He carried no watch, no calendar, no way to know whether it was morning or midnight. His only support was a team above ground to whom he would call when he woke, when he ate, and when he went to sleep. Beyond that, the world outside had no voice. Crawling deep into a glacial cave, he set up a small camp beside an ice wall. Over the next 63 days, he drifted through darkness. The cave was cold, humid, every breath damp. Rocks sometimes crashed from the ceiling. He kept a journal by lantern light, chronicling what he felt, what he remembered, what he thought time might be doing. In those first weeks, the distortions began. He would count seconds aloud to the surface team, asking them to match 120 seconds, 2 full minutes. But those seconds shifted. What felt like 2 minutes took 5. What felt like a half hour might have been much longer. Inside his journal, he scribbled, "I really seem to have no idea of the passage of time." He slept when he was tired. He ate when he was hungry. His internal sense of a day stretched and warped. The cycle he thought might be 24 hours soon became fluid, drifting. Without light or signal, his internal clock ran free. On the surface, researchers logged dates and times. They knew exactly how many hours had passed outside. Underground, Siffre did not. When the 63 days ended, the team told him it was time to come up. He believed there were only about 35 days behind him. He had miscounted more than half. Decades later in Texas, he would try again. Beginning February 14, 1972, Siffre descended into Midnight Cave near Del Rio for a much longer experiment. For 6 months, he lived in a chamber 440 feet below the entrance, entirely cut off from external cues. No calendar, no clock, no daylight. His only connection was a single phone line, used sparingly and only to notify awakening, eating, or sleeping. Every morning, or what he believed was morning, he would call the surface. Lights above him would turn on. He'd perform a series of tasks: blood pressure, recollection tests, cycling on a stationary bike, pressing buttons for mental exercises. Then he'd eat, rest, study the rock, try to read poetry, wait for sleep. In what he perceived as a day, he repeated the cycle, but the pattern changed. As weeks passed, his cycles lengthened. Sometimes he remained awake longer than expected. He slept deeply, then lingered in half sleep. His waking and resting periods pooled into lengths far beyond 24 hours. At times, his day stretched to 48 hours. In the darkness, pacing meant nothing, days blurred. He recorded heartbeat, core temperature, pressure, alertness. He noted when memory began to falter. Names forgotten, dates confused, simple sequences slipping away. He felt time slow down. The mental fog thickened. When he finally emerged September 5th, after 205 days underground, his sense of the world was fragile. The sky was bright. Birds cried. Hours blew past his senses like wind. He recalled thinking his time inside had been far shorter. His internal reckoning was unmoored. What he experienced as months felt like weeks. Externally, his experiment did something far greater. Scientists studying circadian rhythms, chronobiology, and astronaut psychology pored over his data. He had shown that even with no external cues, the human body retains an internal rhythm. But that rhythm is not rigid, it can slow or stretch. Isolated from light and social cues, the body may adopt a free-running cycle longer or shorter than 24 hours. Sifra's biology flexed, sometimes shifting to roughly 24.5 hours, sometimes sliding to much longer periods. In his Texas data, external influence vanished, and the body's natural oscillator revealed itself. Memory and perception also changed. In darkness, time becomes slippery. The brain loses grasp of day and night, events lose order. The longer he stayed underground, the less certain he was of what had passed minutes ago. His results influenced far beyond caves. NASA studied them, imagining how astronauts in space, with no sunrise-sunset cues, might suffer temporal disorientation. Submarines, remote bases, polar stations, all domains where the usual markers of day dissolve, drew insight from Sifra's dark days. In later experiments, Sifra returned underground again, exploring how aging or longer stays would further shift inner clocks. He watched as cycles compressed, elongated, memory blurred, and the mind struggled to tether to an invisible tick. Standing at the threshold of one of his caves, he would see no difference from daylight outside. But inside, many men and women might call half a year a few weeks. Inside darkness, time is no longer a path but a mist. For Michel Sifra, the cave was not just rock and silence. It was a crucible for time itself, where the body, deprived of external anchors, shifted into its own orbit. The cave became his ally and enemy, a realm without clocks, where perception, memory and biology wrestled with the invisible flow of hours. The train that arrived 82 years late. They say that sometimes a train arrives decades late. The tale has gone viral, a ghostly locomotive finally pulling into a station 82 years behind schedule. But there's no evidence this ever truly happened. It is a myth born from misinterpretation, social media, and the romance of lost time. The story usually goes like this. In some remote station, a century-old train emerges from the mists, rolling in on rails long forgotten, arriving 82 years after it was supposed to. Versions claim it was carrying war supplies, prisoners or letters, but when we dig into archives, newspapers, railroad logs, there is no credible source. No historical record, no official report, no corroborated witnesses. That ghost train remains a phantom in the traffic of legend. How does a myth like this grow? Part comes from the appeal of time warps, the idea that time might allow something to slip through, to reappear. Part is from journalistic drift. Once one blog repeats the tale, others echo it without verification. Sometimes a day is misstated, a schedule misread, or a figurative speech taken literally. Soon, the story has wings. Before turning to something real, we must dismantle the legend. No railway archive in Britain, in India, in Russia, or Latin America shows a train overdue by 82 years. No transportation ministry has logbooks showing Mithras train 82-year late arrival. No local newspapers from the alleged station show astonished crowds or inquiries into anachronistic arrivals. A story that dramatic would leave footprints, none exist. In 2019, a claim circulated that a train in Arizona had arrived from 1937. But when pressed, every source traced back to a single unverified post on a social site. It turns out to be a modern ghost tale, dressed in old photographs and crafted in the language of mystery. The infrastructure of real railroads demands maintenance, schedule logs, and radio dispatches. Nothing supports a train time traveller arriving after 8 decades. Yet the power of myth is strong. To propose a train whose schedule spans generations feels like witnessing time itself fray. But facts matter. And in one real story, a delayed train car, a freight wagon, not a full train, truly went missing for years before eventually reaching its destination. That is where our curiosity lands. In India, in November 2014, a goods wagon numbered 107462 was booked by Indian Potash Limited. The wagon carried fertiliser, diammonium phosphate, across more than 1,300 kilometres from Visakhapatnam to Basti in Uttar Pradesh. On paper, it was a routine freight run. But when the other wagons arrived, this one was gone. Its tracks, its path, vanished. AP, Hindustan Times, Times of India. For months, the consignor, Ramchandragupta, waited and followed up. Railway officials looked into the matter. Some said the wagon might have detached due to a technical sick fault. Perhaps it was sent to a yard for a repair. Others said it had been parked at some intermediate terminal, overlooked, mistracked or misfiled. But none could tell precisely where it went. 3 years later, on July 25, 2018, railway employees discovered that very wagon at Basti station, the same destination where it had been booked in 2014. The freight by then was worthless. The fertilizer had rotted, the bags decayed, the cargo expired. The wagon sat unmoved, returned to its place at last. Hindustan Times, New Indian Express, Times of India, Economic Times. When it showed up, the railway was surprised. Officials said they were launching an inquiry to trace what path it took, which yards it spent time in, and how it went unclaimed for so long. The consignee declined to accept the degraded fertilizer, seeking instead compensation. The content was worthless, but the wagon's journey became a curious case of extreme delay. This was not a full train, not a ghost train, and not 82 years late. But it is real. It's a case where a piece of the rail network disappeared into administrative or operational limbo for years, only to be rediscovered later. It reveals how complex large railway systems can lose track of their own cars. Investigators noted that sometimes wagons detached from trains for maintenance, or were declared sick, meaning unsafe, then parked in yards awaiting repair. If records aren't updated or if the yard is remote, tracking can fail. Sometimes no one notices until someone matches a number. The wagon 107462 may have drifted through several stations, yards, records unlabelled or forgotten until it resurfaced. The timeline is slow, untidy. A booking in 2014, no sign in 2015, 2016, 2017. In mid-2018, the wagon appears silent at Basti. The railway system as a whole didn't see an 82-year gap. But for that cargo, for that number, the delay was long, strange and maddening for those expecting delivery. What this case shows is not a time warp, but an administrative void. The processes of tracking, communication, inventory, yard logs failed. The railway network is immense, with thousands of wagons, multiple zones and shifting control. One lost wagon can slip through the seams. Contrast that with the ghost train myth, a full locomotive, crewed, scheduled, operating invisibly for decades. That is fantasy. But a freight wagon slipping, drifting, misfiled, forgotten, that is plausible. And it actually happened. So in this chapter we step through both the myth and the fact. We begin with the ghost story, test it against archival expectation, find it wanting. Then we move to India's real delayed wagon, numbered, traced, rediscovered. A curious case of real temporal loss, though caused not by relativity but by bureaucracy, oversight, and the immense scale of rail systems. This is no mystical arrival, it is human error, delay, and redemption by record. Pioneer anomaly. In the late 1970s and early 1980s, engineers tracking two spacecraft noticed something odd. The two probes, Pioneer 10 and Pioneer 11, were not doing exactly what celestial mechanics predicted. Tiny deviations appeared. Over decades, the difference accumulated. This became known as the Pioneer anomaly, a mystery that haunted astrophysicists for years. Pioneer 10 launched in 1972, Pioneer 11 in 1973, sent to explore the outer solar system, Jupiter, Saturn, and beyond. After their planetary encounters, they continued outward into deep space, their thrusters mostly silent, gliding in near vacuum. Their navigation was precise, relying on Doppler shifts of radio signals from Earth. As they passed roughly 20 astronomical units from the Sun, data began to show something strange. They seemed to be slowing more than expected. That means they were a little closer to the Sun than predicted, as if a tiny force tugged inward. This extra deceleration was minuscule, on the order of 8.74 x 10, 10, 8, 74, 10, 10 meters per second squared. That's almost unimaginably small. But over years, that little extra pull added up, shifting predicted positions by tens of thousands of kilometers. Scientists asked, what unseen force was acting on these probes? Many ideas were floated. Maybe there was a drag from interplanetary dust. Maybe there were gas leaks from the spacecraft. Maybe our understanding of gravity was incomplete. Some proposed exotic physics, modifications to Newton or Einstein at large distances, new forces, dark matter halos, even cosmic expansion effects. None fit cleanly. As the anomaly persisted, the case grew colder. The mystery deepened. Navigation teams combed through archived telemetry, historic temperature logs, component designs, even the orientation of the probes and the aging of their power systems. It looked like a cold case, a small puzzle in the vastness of space waiting for clues. One crucial clue: both pioneers carried radioisotope thermoelectric generators, RTGs. These generate electricity by decay of radioactive material and in the process release heat. That heat must leave the spacecraft somehow. In a vacuum, heat leaves by radiation, photons carrying energy. If those photons are emitted symmetrically, there's no net push. But if the emission is a bit asymmetrical, the spacecraft might get a tiny nudge, a recoil force from thermal photons. Researchers built increasingly detailed thermal models of the probes. They gathered flight telemetry, component maps, materials emissivity, insulating blankets, reflection surfaces. They modelled conduction, radiation, reflection effects, and how parts warmed, cooled, and re-radiated heat. Their work used finite element modelling and precise boundary conditions. By 2012, a team led by Slava Turyshev and others published a paper showing that when properly accounting for anisotropic thermal radiation, the effect could fully explain the anomaly. The direction, magnitude, and decay of the extra acceleration matched what the models predicted. In other words, the apparent anomaly vanished once the thermal recoil was included. The key is that parts of the spacecraft that produced heat, electronics, power systems, radiated more photons in some directions than others. Some heat reflected off structures such as the back of the antenna and was preferentially sent outward, producing a tiny push inward. Over time, as the heat output declined, radioactive decay, aging, the extra recoil effect diminished. Observations matched that trend. The result, the Pioneer anomaly, was not a sign of new physics. It was a case of engineering nuance, overlooked at first, but resolvable through careful modelling. The extra force was real, but it came from inside the spacecraft, not from beyond. To understand it fully, we must step through the timeline. The anomaly was first noticed in the early 1980s, but only seriously studied in the 1990s. Navigation teams compared modelled motion, gravity, solar radiation pressure, solar wind, with Doppler signal tracking. The residuals, tiny but systematic, persisted. Over years, archival data was recovered, telemetry reconstructed, spacecraft thermal history re-examined. New methods in computational modelling matured. Teams from NASA's Jet Propulsion Laboratory, academic groups, and independent physicists all reanalyzed the data. They found that earlier estimates of thermal recoil were incomplete, lacking high-fidelity models of reflections, structure shadows, and changing heat paths over decades. When they recalculated, adjusting models for telemetry, thermal expansion, material degradation, and surface properties, their predictions for the recoil force matched the observed acceleration. The anomaly disappeared within error margins. The final papers declared that once thermal recoil is accounted for, there is no statistically significant unexplained force left. Thus, a decades-old space mystery found its resolution not in exotic new physics, but in detailed accounting of heat, materials, and reflection. The Pioneer probes drifting in the void taught us a lesson. In extreme environments, even minute internal effects can masquerade as cosmic anomalies. Long-delayed radio echoes. Imagine you speak into a radio, and then hear your own voice back. Not in a fraction of a second, but several seconds later. As if your words had wandered through distant space or tunneled through hidden circuits. These are long-delayed echoes, or LDEs. Radio reflections that return not in milliseconds, but in full seconds after the original transmission. The first recorded whisper of this oddity came in 1927. Jürgen Hals, an amateur radio operator near Oslo, Norway, was listening to shortwave signals from PCJJ, a Dutch transmitter in Eindhoven. He heard the primary echo, a known reflection, but then, about 3 seconds later, found a faint echo of the same signal. He wrote to physicist Carl Stormer, "I repeatedly heard a weaker echo about 3 seconds after the principal echo had gone." He could not explain the source, but confirmed that what he heard was real. Because the phenomenon didn't follow the rules of ordinary radio reflection, It puzzled scientists. Radio engineers and physicists listened, measured, debated. Echoes that bounce off ionospheric layers typically return in milliseconds, 100th or 1000th of a second. But echoes delayed by seconds defied standard propagation models. Over the decades, reports of LDEs appeared sporadically. They were irregular, fleeting, often reported by radio amateurs experimenting with HF high-frequency bands. Sometimes the echo delay was 2 seconds, sometimes 5, occasionally even more, but the pattern never became common enough to settle on one mechanism. Many theories floated. Some suggested that radio waves might enter ducts in the Earth's magnetosphere or ionosphere, travelling along magnetic field lines, reflecting back, refracting, until occasionally returning long after the original signal. In other models, signals could be trapped between ionospheric layers and bounce multiple times until one path broke out. Some even speculated that solar plasma clouds or disturbances in Earth's plasmasphere played roles. One interesting idea: mode conversion. Here, the transmitted radio wave interacts with plasma in the upper ionosphere, turning partly into plasma waves, then back into radio waves later, returning to the sender after delay. These paths can elongate the round trip, sometimes by seconds. Another concept is multiple Earth-Moon reflections. The radio wave bounces to the Moon, returns to Earth, reflects again, and then returns to the Moon before coming back. But the timing seldom matches exactly what's observed, and the signal strength often decays too much for that to be viable in many cases. More recent efforts measure echoes delayed between 2 and 8 seconds most often, with some reports beyond that. Studies have tried to correlate echo events with solar storms, geomagnetic disturbances, ionospheric anomalies. Some echoes coincide with periods of solar activity or auroral events, suggesting a link to Earth plasma environment. Still, none of these theories fully matches all observations. The irregularity, the variation in delay time, and differences across frequencies resist a single explanation. For some LDE events, the predicted path length or energy budget makes the suggested route implausible. The anomaly remains partially unresolved, a ghost in radio propagation. Technically, an echo delayed by more than 2.7 seconds is often considered a long-delayed echo, longer than the time it would take for a radio wave to go from Earth to the Moon and back. In other words, even lunar bounce can't fully account for many LDEs. Over the years, radio scientists have catalogued dozens of LDE cases, sometimes cross-verified by multiple stations, with different frequencies and varying signal strengths. They compare logs, attempt to repeat experiments, adjust frequency, power, and path directions, but the phenomenon resists consistency. Occasionally, skeptics suggest hoaxes or instrumentation errors. Some echoes could come from mistuned receivers, reflections inside equipment or cables, misidentified signal mixing, or delayed local echoes in circuits. Radio amateurs and professionals both urge caution. Not every reported LDE is trustworthy. Some repeaters or equipment faults mimic echoes. Yet among many well-documented cases, the echo is real. There is no simple send and return explanation. In 1979, researcher D.B. Muldrew published a paper, Generation of Long-Delay Echoes, exploring propagation modes, geometry, and plasma interactions. He and others mapped how radio waves might linger in the upper atmosphere or magnetosphere before returning. More modern reviews consider a set of likely routes: ducting in magnetospheric channels, reflections inside plasma irregularities, coupling to plasma waves, or travel along field lines. Some models use mixed paths, part reflection, part conversion, part travel through trapped plasma. One group, led by Professor Sverre Holm, outlined 5 most likely explanations, combining theories on reflection, conversion, field line propagation, ionospheric ducts, and scattering in plasma clouds. Every model explains some cases, but none covers all. Because LDEs occur at different frequencies at different times and with different delays, it's likely that multiple mechanisms play a role. The Earth's space environment is dynamic, often messy, full of currents, magnetic fields, charged particles, changing density. A signal might pluck one path one time and a different path another. From the voice of an operator in 1927 to skilled radio experimenters in the mid-20th century, long-delayed echoes have haunted the airwaves. They remain a challenge, a reminder that even the empty space above us can hide subtle surprises. As you listen for that delayed echo, seconds later, You sense it, an echo not just of sound but of unknown pathways, of signals wandering in the plasma sea, of the invisible architecture of Earth's upper realms. Houston, we have a 2.6-second lag. When Houston speaks, the moon does not answer right away. Between them, space swallows 2.5 seconds. That pause, about 2.6 seconds round trip, is the sound of distance itself. It's the time light takes to cross nearly 400,000 kilometers from Earth to the moon and back again. You can hear it in the recordings of Apollo missions. In every exchange between mission control and the astronauts, that gap quietly marks the separation between two worlds. Houston says something, and then there's stillness, a frozen breath, before the reply. Sometimes you can even hear Houston's own words echoing back through the astronauts' microphones, delayed by the round trip across space. During Apollo 11, when Armstrong and Aldrin stood on the lunar surface, that delay carried every heartbeat of their conversation. A question from Earth would take just over 1 second to reach them. Their answer, travelling back at the same speed, added another 1.5 seconds. Two voices separated by space and time, stitched together by radio waves travelling at light speed. The path begins in a control room on Earth. Engineers key a microphone, and a signal surges through transmitters and massive dish antennas. It rises through the atmosphere into open space, racing across the void toward a silver disk 500,000 kilometers away. It hits the lunar module's antennas, enters the onboard radio systems, and comes out as a faint voice in the astronauts' headsets. When an astronaut speaks back, the process reverses. His words become an electrical current, then a radio wave, leaping away from the lunar surface. It races toward Earth, where deep space antennas in California, Spain, or Australia catch it, amplify it, and beam it into mission control. All of that happens in about 2.6 seconds. The delay is constant, unavoidable, and perfectly predictable. If you listen closely to unedited NASA tapes, you can hear this rhythm clearly. A voice in Houston says, "Eagle, do you copy?" 2 heartbeats later, the echo of that same phrase returns, faintly, from the astronauts' open microphones. Then another 0.5 second of silence. Finally, the reply, "Roger, Houston, loud and clear." That gap is the echo of space. Pure physics made audible. The delay shifts slightly during the mission. The moon's orbit is not a perfect circle, so the distance changes every day. When the moon is closest, the delay shortens to around 2.4 seconds. When it drifts farthest, it stretches closer to 2.7 seconds. Even those small variations can be measured in the timing between command and response. For engineers and flight directors, that delay had practical consequences. They had to learn to speak in rhythm with it, to give instructions, then wait. They couldn't interrupt, couldn't overlap. If someone on Earth spoke too soon, their voice would collide with the astronauts' reply halfway between worlds. Every exchange required patience. During the Apollo 12 mission, recordings captured a perfect example, a delay measured at about 2.7 seconds. When Houston's words were transmitted to the moon and inadvertently fed back through the astronauts' radio circuits, the echo was caught on tape. The sound carried 2 versions of the same phrase, one live, one returning almost 3 seconds later. It was an unintended experiment confirming the exact distance to the moon. Later, physics students and engineers analysed these recordings. By measuring the gap between the original signal and the echo, they could calculate the moon's distance to within a few hundred kilometres, the same value astronomers knew from laser measurements. The delay itself had become a ruler across the sky. People often ask why live broadcasts from the moon in 1969 seemed so smooth, with little pause between question and answer. In truth, television networks and NASA editors trimmed many of the silences for broadcast. The real communications, in raw form, include that constant 2.5 second heartbeat of emptiness. Behind every roger and every copy that was that span of waiting. A moment where neither side could speak or hear, both suspended between send and receive. It was not a flaw, but a fact of the universe. Nothing, not even radio light, can outrun the finite speed of light itself. In the recordings, you can hear Houston's calm precision followed by a pause long enough to feel strange. Then, a crackle and the distant reply. That silence is space. That silence is distance. It is the sound of Earth and Moon connected by an invisible thread of electromagnetic energy stretched to its limit. Every Apollo mission carried that same invisible delay. Every word, every call sign, every confirmation had to pass through that time window. The engineers at Mission Control built their operations around it. They knew that if something went wrong, the delay would always be there, a constant reminder that help and response could never be instant. That 2.6-second lag became part of the rhythm of human exploration beyond Earth. It's written into the data, the audio, the cadence of every exchange. You can hear it on the tapes, in the pauses, in the echoes, in the calm patience of voices separated by space. It's not an error, it's the voice of light itself, taking just a little longer to come home. 8-minute sun, every morning when you see the sun, you're seeing a moment from the past. What shines on you now actually left the sun 8 minutes and 20 seconds ago. That delay is the time it takes light to cross the gap between sun and Earth, and in that span you're looking at sunlight that is already history. To understand why, we begin with distance. Earth orbits the sun at an average of about 150 million kilometers. Light travels at a constant speed, about 300,000 kilometers per second. Divide distance by speed and you get time. The result is roughly 500 seconds, that is about 8 minutes and 20 seconds. So when a photon of visible light escapes from the sun's visible surface, or photosphere, and travels through space, it takes that much time to reach our eyes. The moment we bask in daylight, we are witnessing the sun as it was over 8 minutes ago. This is more than poetic. It is a literal time delay baked into the cosmos. The sun is not lighting us in real time, it is lighting us from a past moment, delayed by the vastness of space. Of course, Earth's orbit is not a perfect circle. Sometimes we are a bit closer, sometimes a bit farther, depending on where we are in the elliptical path. That means the light travel time can vary, sometimes slightly less than 8 minutes 20 seconds, sometimes a bit more. But there's another hidden twist. The photons we see do not originate from the sun's core straight away. They're born deep inside in nuclear reactions. Each photon is absorbed, re-emitted, scattered, and redirected many, many times as it works its way outward through the dense layers of solar plasma. That internal journey can take thousands, even tens of thousands of years before the photon reaches the surface and begins its 8-minute dash to Earth. What that means is when we look at sunlight, we see a photon that was born eons ago in the core, finally liberated after a long internal path, then sent across space. The 8 minutes is just the last leg of a very long journey. Because of that, the sunlight you see now actually combines two time delays, the internal solar diffusion delay and the light travel time. But what's easiest to measure, what we often talk about, is that interplanetary stretch, the 8 minutes 20 seconds across space. The consequence is profound. In effect, we always see every celestial object not as it is now, but as it was in the past. The further the object, the older the snapshot. The sun, being near, is an 8-minute memory. A star 1,000 light years away is a 1,000-year memory. This principle has surprising consequences. If, hypothetically, the sun were to vanish, a thought experiment, not a real possibility, we would not see it go dark immediately. The sun's light would continue to reach Earth for those 8 minutes and 20 seconds before disappearing entirely from view. Astronomers use this light travel time all the time. When they observe changes on the sun, sunspots, flares, coronal mass ejections, they're always seeing events that already happened, delayed by those minutes. The timing of observation, prediction and effect must always account for that lag. In past centuries, astronomers noticed that when the sun's rotational features changed, there was a slight but measurable delay in when Earth observers saw them. That helped them refine models of solar motion, rotation periods, and calibrate instruments. It also affects how we interpret distance and motion among celestial bodies. For example, when we measure the position of a planet, we measure where that planet was, not where it is. We correct for light travel time so our calculations reflect true motion. In everyday life, this light delay doesn't feel dramatic, but it is always there. Sunrise, sunset. The timing we set on clocks is already behind by those minutes. Noon is never truly noon with the sun overhead. It is always 8 minutes and 20 seconds behind. There is also a subtle harmony. Gravity's influence, according to general relativity, propagates at light speed too. That means the gravitational pull we feel from the Sun is also delayed in a sense. We feel the Sun's gravity from where it was 8 minutes ago, though because of relativistic corrections, planetary orbits remain stable. What's surprising is that despite the lag, the solar system behaves as if gravity were instantaneous, because corrections in relativity cancel out what we might expect to see as orbital instability. The geometry of space-time ensures orbits remain stable, even with finite signal speed. When you step outside and feel warmth or see daylight, know this: you're standing in sunlight that left the sun before your ancestors woke that morning. The light you see is history, reaching forward across space and time, delivered at the speed of light but never instant. Every dawn is delayed, every photon arrives late, every sunrise is already in the past. Shapiro delay. Imagine you send a radio signal toward Venus or Mercury during an alignment with the Sun. You expect it to bounce and return, but the signal takes slightly longer than your simple calculations allow. Why? Because gravity itself is slowing time for that signal. That tiny extra delay is called the Shapiro delay, a subtle bending of time by mass. In 1964, astrophysicist Erwin Shapiro predicted that electromagnetic signals passing close to a massive object would be delayed. According to general relativity, space and time are warped by mass. Light doesn't take a straight line through that warped space. It bends and strolls through a deeper gravitational potential. The closer a signal passes to that mass, the more time it spends in warped space, and the slower it appears from the outside. That is, signals that skim near the Sun should arrive back later than predicted by classical physics. Shapiro proposed testing this by bouncing radar signals off Venus or Mercury when they lie on the opposite side of the Sun, so that the path would pass near the solar surface. The extra delay predicted would be small, microseconds, but measurable with precise equipment. This effect sometimes is called the fourth test of general relativity, alongside the classic tests: Mercury's perihelion precession, gravitational redshift, and bending of starlight around the Sun. The Shapiro delay added another layer: time itself slows in gravity. Here's how the experiment works. You send a radar pulse from Earth aimed at a planet on the far side of the Sun. The signal passes close to the Sun, then reaches the target, reflects, and returns along approximately the same path. Because of the Sun's gravity, the signal doesn't travel at c all the way. The curvature of space-time means your external measurement sees the signal take extra time. That extra is the Shapiro delay. Over time, physicists carried out these radar echo experiments many times. They timed signals to Mercury, Venus, Mars, spacecraft, and landers. The observed round-trip time was consistently longer by a small but detectable amount when the signal path nudged near the Sun. These delays matched what general relativity predicted. A success for the theory. The extra delay is not huge, but for a path grazing the Sun, it can measure several hundred microseconds. That is equivalent to the signal being delayed by tens of kilometers in light distance. If you imagine light itself slowed, it's akin to the signal having to travel through slightly thicker time. A modern test used the Cassini spacecraft when it was nearly behind the Sun, as seen from Earth. By measuring the radio link in high-frequency bands, K-band, scientists confirmed the Shapiro delay to very high precision, leaving little room for deviation from relativity's predictions. To translate it, gravity doesn't just pull mass, it drags time. Light passing through that gravity feels the pull in its timing. The signal spends more proper time in the gravitational well than if the mass weren't there. Mathematically, the delay can be described by an equation involving the gravitational constant, the Sun's mass, the distances involved, and a logarithmic term depending on how close the signal passes the Sun. The closer the path, the greater the delay. Let me walk you through a simplified version. The delay dt is proportional to 4 gm c 3, 4 gm/c 3, times a log expression involving the distances from the Sun to Earth, the Sun to the planet, and the impact parameter, the signal's closest approach to the Sun. The logarithmic part means the delay grows more slowly with distance. It's not linear, but it is sensitive to the geometry. In practice, observers compare the expected round-trip time, in absence of mass curving space, with the measured time. The difference is the Shapiro delay. That is repeated for different alignments to map how delay varies with closest approach. One classic case involved radar echoes to Venus when the planet was almost directly behind the Sun from Earth. At superior conjunction, the path passes near the solar limb, maximising the Shapiro delay. Measurements showed the echoes took a few hundred microseconds longer than expected, precisely in line with theoretical predictions. As experimental techniques improved, the precision of tests improved. Radar ranging to planets and spacecraft, laser ranging to the moon, and timing of signals in binary pulsar systems all incorporate Shapiro delay effects. It's no longer a small curiosity. It is a necessary correction in high-precision astronomy. Even spacecraft point navigation and time synchronization must include gravitational time delay. Without correcting for Shapiro delay, ranging errors would accumulate. Deep space missions, planetary ephemeris, and gravitational wave timing models all factor in gravitational time delay when signals pass near massive bodies. Beyond the solar system, the effect is seen in binary pulsars. When pulses from a pulsar pass near its companion star, they travel through gravitational wells and get delayed. The timing variations help measure masses, test relativity, and map space-time curvatures. So, in the story of light and gravity, Shapiro delay is a bridge, a way to hear time stretch. A signal passes close to mass, slows in coordinate time, and comes back late. The delay may be tiny, but it is real, measurable, consistent. And every time we send a radar ping past a gravitational well, the echo whispers of warped space-time, the twin quasars echo. Imagine a distant quasar, a spectacular beacon in the early universe whose light takes billions of years to reach us. Now imagine that light splitting into two paths, travelling around a massive galaxy's gravity and arriving at our telescopes at different times. That is the phenomenon of gravitational lensing, and in one special system known as the twin quasar, Q0957 plus 561, we can actually hear the cosmic echo. One image leads by about 417 days. The twin quasar was discovered in 1979. At first glance, astronomers saw two quasars remarkably close together, almost identical in spectrum and redshift. It looked like a pair, yet there was something uncanny about them. As studies progressed, it became clear they were two images of the same quasar, distorted and delayed by a lensing mass between us and the quasar, an intervening galaxy and galaxy cluster warping spacetime in between. Thanks to that lensing, the quasar appears as image A and image B, separated by a few arcseconds in the sky. Each light path winds through a different trajectory around the lensing mass. One path is shorter, passes through slightly different gravitational potentials, and reaches us earlier. The other is longer, possibly weaving through denser fields or additional mass concentrations, arriving later. That delay between the two images is a cosmic time lag, a built-in clock. Astronomers have measured that delay to be about 417 plus 3 days. That means a flare, brightness change, or any intrinsic variation in the quasar will appear in image A, then show up again in image B nearly 14 months later. The delay corresponds to light taking extra path length or slower routes through warped spacetime. This is not science fiction. We observe it in light curves. For years, teams monitored the brightness of both images nightly. They looked for patterns, ups and downs in brightness that repeated after some lag. When features in image A matched features in image B after about 417 days, that time shift confirmed the delay. The method is straightforward in concept. You graph the brightness of A over time and separately that of B. You shift one light curve forward by some days until the patterns align. The best match gives you the delay. Over decades, repeated monitoring in optical bands, GR, and in radio wavelengths refine the value. Some studies report slight band differences, but overall 417 days is accepted. Why does this delay occur? Because gravitational lensing does more than bend light. It warps space-time and dictates travel time. Even if two paths are nearly the same length geometrically, the difference in gravitational potential, curvature, and path geometry means one photon feels more delay than the other. The deeper the light dives into gravitational wells, the slower its coordinate time becomes. We can think of the lensing galaxy and its cluster mass as sculpting the paths. One path might curve close to the galaxy core, encountering strong potential, extra gravitational time dilation. The other path might skirt further, avoiding dense matter but covering more distance. So the difference in arrival time is the result of geometry and gravitational delay combined. In radio wavelengths, similar delays appear. Observations at 4 cm and 6 cm radio bands show consistent time lags in their flux variations of the quasar images. Because radio emission often comes from jets or cores, the paths may sample different emission regions, but the delay persists. The radio-determined delay magnitude is broadly consistent with optical estimates. That 417-day clock gives astronomers a tool beyond curiosity. The delay serves as a measurement of Hubble constant, the expansion rate of the universe, mass distribution in the lensing galaxy, and the geometry of intervening mass. By modelling the lens, the delay becomes a parameter linking cosmology and gravitation. Yet it is not without challenges. Microlensing by stars in the lens galaxy can modulate the brightness of one image independently, altering fluxes or smoothing peaks. That can distort light curves and complicate correlation. Some fluctuations might come not from the quasar itself, but from microlensing events along one path. Observers must distinguish intrinsic variation from microlensing noise. Other uncertainties include dust extinction, differential absorption along paths, and variations in the intergalactic medium. Also, slight errors in timing, gaps in data, or observational noise can shift delay estimates by days. Multiple studies across decades have sometimes found slightly different delays, but most cluster around 417 days. In one 2012 optical monitoring campaign lasting 5.5 years, researchers compared G-band and R-band delays. They found that R-band delay exceeded the 417-day baseline by about 3 days in some epochs, hinting at wavelength-dependent effects or lens substructure interfering with light paths. Even so, the 417-day figure remains a benchmark. Because of its relative brightness and longevity, Q0957 plus 561 remains one of the most studied lens systems. It was among the first where time delay was reliably measured, validating lensing theory observationally. It showed that gravity can turn a galaxy into a cosmic prism, splitting light into multiple echoes. When you look skyward, when you observe a quasar flicker, imagine that behind it is a vast interposed galaxy curving light and time. One flash here, another flash months later elsewhere. The sky holds hidden echoes, cosmic delays, and twin images speaking across space-time. In Q0957 plus 561, gravity itself became the cosmic timekeeper, Essen-Refstal, a supernova that reappeared on schedule. Light from a single supernova can echo across time. In late 2014, astronomers peered deep into the galaxy cluster, Max J 1149.6 plus 2223, and discovered something extraordinary. An exploding star, Essen-Refstal, showing up as 4 separate images around a foreground galaxy. The explosion's light had been lensed, bent and delayed by gravity, giving us not one view but multiple staggered echoes of the same cosmic flash. The discovery felt like catching a rerun in the sky. Supernovae are typically transient, brilliant for weeks or months, then fade. But in this case, the light had already taken multiple routes through the cluster's gravitational field. Some paths were longer, some deeper in potential wells, some would reach us later. Theoretical models even predicted that the supernova would reappear again, a delayed 5th image arriving at a different spot in the cluster months later. In November 2014, Hubble captured the 4 initial images, labelled S1 through S4, forming something like an Einstein cross around a galaxy inside the cluster. The lensing mass of the cluster and a galaxy within it had distorted and magnified the light. The 4 images were simultaneous in Earth time, but arrived staggered by small delays, days or weeks, depending on path geometry and gravitational delays. Before repeating, astronomers built detailed mass models of the cluster. They mapped dark matter, stellar mass, cluster-scale halo structure, and projected potential fields. These models predicted that one more image of Essen-Refstal should reappear about a year later, at a different position, delayed by hundreds of days from the first observed set. The exact timing and brightness were uncertain, depending on which model was correct. Then, in December 2015, the prediction came true. Hubble observed a new bright spot at the predicted location, the 5th image, often called SX, arriving on schedule. The timing and flux of this reappearance matched blind model predictions within margins. In other words, astronomers forecasted where and when the supernova would reappear, and they were right. What does that mean? The supernova's light is acting like a cosmic clock. its multiple images are echoes. One echo arrives early via a shorter or less curved path, another comes later via a more circuitous, gravitationally deeper route. The delay is real, measurable, and tied to the geometry and mass of the lens. The delay between the first set S1, S4 and the fifth image SX is about approximately 417 days. That prolonged wait is not fanciful, it encodes how much extra distance or gravitational time the light had to traverse. The models that correctly predicted it did so by calculating how lensing warps both space and time. Each path's travel time depends not just on spatial length, but on gravitational potential. This case fulfilled a prediction first proposed decades earlier. In 1964, Norwegian astrophysicist Sjur Refsdal suggested that time delays from multiple images of a lens supernova could be used to measure the universe's expansion, Hubble constant, and mass distribution in lensing structures. The event was named in his honour for realising that vision. After the reappearance, scientists used the delays and magnification factors to constrain not only the cluster's mass distribution, but cosmological parameters. Some studies estimated the Hubble constant from the time delays in SN Refsdal using cluster models and lensing theory. The data also helped refine which mass models were viable. Some predictions overshot timing or brightness, others undershot. The match between observed and predicted reappearance narrowed uncertainties in dark matter distribution, substructure in the cluster, and the gravitational potential of galaxies inside the cluster. Beyond that, the event showed the predictive potential of lensing theory. This was the first time a lensing prediction of a supernova's reappearance was tested successfully. It showed that gravity can turn an explosion into a delayed echo across years. The sky, in that region, held a looping replay of a single dramatic cosmic event. When you imagine that distant star exploding billions of years ago, then see it again after more than a year of waiting, you realize that light is not just a journey, it is a storyteller. Each path, each delay, is a chapter through gravity, through cosmic structure. SN Refsdal's echo let us hear a story in parts, played out across space-time. Aluminum ion clocks on a staircase. On a staircase just a foot tall, scientists made time shift. At NIST in Boulder, Colorado, physicists perched one ultra-precise atomic clock just 33 centimeters above another. And when they compared them, they found the higher clock ticked just a little bit faster. That minuscule difference is not illusion. It's gravitational time dilation, verified on a human scale. The clocks are among the world's most precise. Each is a quantum logic clock built around a single aluminum ion. Lasers trap and cool that ion, holding it in place. The ion's internal energy levels vibrate at a known frequency. Transitions between those levels act as the ticks of the clock. The mechanism is so steady and precise that these clocks would lose 1 second in billions of years under ideal conditions. To test relativity's prediction, the researchers placed one clock 33 centimeters higher than the other in the laboratory environment. They linked them via a phase-stabilized optical fiber, so signals and comparisons remained clean and undistorted. Then they watched. According to Einstein's general relativity, time passes more slowly deeper in a gravitational field. The closer you are to Earth's center, the stronger gravity you feel, and the more that clock of yours is stretched. So a clock elevated slightly should tick faster. That minute difference is called gravitational redshift in time. What they saw matched the theory. The upper clock ran faster by a fractional frequency difference on the order of 10 elevated to -16. That tiny shift corresponded precisely to what relativity predicted for that height difference in Earth's gravitational field. In simple terms, lift a clock by 33 centimeters and it ages a little more in the same interval than its lower twin. The result is profound because the effect is so incredibly small. The clock elevated by less than a foot gains time at a rate detectable only because these clocks are extraordinarily precise. Older clocks, cesium fountains, rubidium standards, couldn't resolve that shift, but these aluminum ion quantum logic clocks can. From the data, they computed that gravitational time dilation at that height accounts for the difference. That experiment wasn't just a curiosity, it confirmed that we live in a world where even tiny height changes matter to time itself. To carry this out, the experimenters had to control many details: environmental effects, temperature drift, magnetic fields, vibrations, had to be minimized. The optical fibre link had to carry signals cleanly so the phase relationships between clocks remained stable. The traps holding the ions had to be identical except for height. Systematic biases had to be cancelled. Even more, they verified that velocity time dilation, if either clock moved slightly, was negligible. The shift they observed could not be explained by motion. Only gravitational potential difference remained. This experiment is sometimes described as proving that your head is older than your feet, because if you stand on the ground, your feet are deeper in Earth's gravity. Your head is a bit farther out. Over long periods, your head ages faster, ever so slightly. The NIST work showed that in just 33 centimeters, a clock behaves differently. Earlier gravitational redshift tests compared clocks placed on towers, mountaintops, or aboard rockets. The Pound-Rebka experiment of 1959 used gamma rays over vertical distances, confirming gravitational redshift in photon frequency. Other tests raised clocks hundreds or thousands of meters, but this staircase experiment shrinks that scale to a human step. It shows that relativity is not only for stars, planets, or black holes. It's present in your room, your height, your posture. The effect is real and measurable with the right tools. Because these clocks are so sensitive, future applications open. We might map Earth's gravity field with clocks, measuring height differences not by leveling or GPS, but by time itself. You could sense subterranean mass anomalies, water flows, underground cavities, by how they distort clock rates. This is sometimes called relativistic geodesy. In fact, scientists propose networks of optical clocks across a country linked by optical fibres, measuring gravitational potential differences via tick rates. Elevation differences of mere centimetres could be mapped by clock comparisons. The 33 centimetres test is a milestone. It proves that within a lab you can measure gravitational time dilation at everyday scales. Before, relativity's predictions seemed remote. Now we see them at eye height between adjacent steps. In this realm, height is time. Two clocks centimetres apart no longer keep identical time, and our physics tells us why. Gravity warps space-time, so time itself changes with position. The NIST aluminum ion clocks transformed a staircase into a lab, where Einstein's prediction becomes audible in the frequency difference. A new clock for the moon? Time on the moon doesn't march in the same beat as on Earth. A clock placed on lunar soil runs faster, by about 58.7 microseconds per Earth day. That tiny difference may seem negligible, but for future lunar missions, it becomes essential. That discrepancy is pushing space agencies to define a moontime reference, a time standard just for the moon. The reason lies in gravity. According to Einstein's theory, clocks deeper in a gravitational field tick more slowly relative to clocks in weaker fields. Earth, being more massive, produces stronger gravity at its surface than the moon. Thus a clock on the moon, where gravity is weaker, experiences less gravitational slowing and so accumulates time slightly faster compared to an Earth clock. In technical proposals now underway, the inconsistency is not just theoretical. With dozens of missions slated to orbit, land, move, and build on the moon, time synchronization across Earth, lunar orbiters, and surface installations must be precise. If a lunar clock runs ahead by microseconds each day, over time the offset grows. Navigation, communications, docking, timing signals all depend on atomic clocks tuned to the correct frame. To that end, governments and space agencies are collaborating on what is called Coordinated Lunar Time, LTC. The idea: establish a time standard traceable to Earth's universal time, but corrected so that clocks on the moon tick with their own heartbeat. LTC is not a time zone like we use on Earth. It's a coordinate time system, a reference frame for time on the moon. According to policy directives, LTC must satisfy four main requirements. First, traceability to UTC, so Earth and Moon time can be compared. Second, enough accuracy to support navigation, mission timing, and scientific operations. Third, resilience. If lunar hardware loses contact with Earth, the standard must persist. And fourth, scalability, so that the same framework can extend beyond the Moon, to Mars, etc. In theoretical modelling, clocks placed on the lunar equator or surface must be assigned a rate relative to Earth clocks that correct for gravitational and kinematic differences. Researchers Neil Ashby and Bijunath Patla offered a relativistic framework to define coordinate time on the Moon. They calculated that a lunar clock near the equator ticks faster, accumulating approximately 56 microseconds per day relative to Earth's geocentric clock. This aligns with other estimates around 58.7 microseconds per day. That drift matters. A difference of 50 microseconds is already significant in high-precision space operations. For instance, in navigation, a microsecond error maps to hundreds of meters of position error in light travel distance. For docking lunar modules, coordinating relays, or synchronizing orbital assets, those small mismatches could be critical. Because the lunar clock rate is not constant everywhere or every moment, the standard must account for variations. Clocks at different latitudes, different elevations, and orbital states will each have slightly different gravitational potentials or velocities. The LTC model must include periodic terms and corrections to keep clocks aligned across the Moon. Earth's UTC is built from networks of atomic clocks, averaged, corrected, and synchronized. LTC would likely use atomic clocks on the lunar surface, in lunar orbit, and perhaps at stable positions like Lagrange points, all linked by precise time transfer. The clocks would maintain LTC locally, even during loss of Earth contact. In the near term, missions often use Earth-based time, UTC, for simplicity. Lunar landers and rovers record in UTC, and communications translate between frames. But once infrastructure grows, rovers, bases, satellites, mining, long-duration stays, the drift becomes unwieldy. Having a native lunar time standard avoids accumulated mismatches and ambiguity. One public directive underscores the urgency. In 2024, the US White House tasked NASA, along with its partners, to define a lunar time standard by the end of 2026. The idea is that as Artemis missions begin, a shared time framework will already exist. Without it, mismatches in signaling, data transfers, or command timing across spacecraft risks confusion. To build LTC, scientists must integrate relativistic theory, orbital dynamics, gravitational potentials, and clock networks. The clocks must be synchronized initially to Earth time, then drift corrected. Each clock's rate must include formulaic adjustments for lunar gravity, orbital velocity, and positional variation. One proposed step: deploy atomic clocks on the lunar surface and in orbit early in lunar program operations. These clocks would continuously exchange timing signals and apply corrections to maintain LTC. Earth-Moon time conversion formulas would be standardized, so a clock on the Moon and a clock on Earth can interconvert readings precisely. Another complexity: like Earth, the Moon has mass variations, topography, bit of gravitational anomalies. Clocks in a crater, on a mountain, or near mass concentrations will have slight differences in gravitational potential, so local corrections may apply. The LTC design must accommodate spatial variation across the lunar surface. Also, if a lunar clock must survive without contact to Earth for periods, for example during solar conjunctions or communications blackouts, it must maintain the standard internally, no reliance on Earth pinging, so the time grid must be robust, local, and self-consistent. The math is non-trivial. Researchers developing LTC coordinate time frameworks draw from high-precision, relativistic time transformations between solar system barycenter, Earth, Moon, and local clocks. Some papers derive transformations indicating a secular drift of approximately 56 microseconds per day plus periodic terms from orbital ellipticity and gravitational perturbations. In simplified form, LTC will tick slightly faster than Earth time. Over one lunar month, 29.5 Earth days, the offset accumulates to on the order of 1.7 milliseconds. Over years, that drift compounds unless corrected. That's precisely why LTC is needed from the start of sustained lunar operations. When clocks run asynchronous between Earth and Moon, commands sent at a given UTC timestamp might arrive at a lunar target with an offset. When lunar systems reference UTC internally but LTC externally, conversions become necessary. But ideally, systems on and around the Moon will operate naturally in LTC, minimizing translation errors and mismatches. One way to visualize it: Earth time is like a river running through Earth's gravity well, slightly slowed. The Moon time is that river untethered, running a bit freer, a bit ahead. But across the system we'll keep a dial so both flows can be compared. In the coming years, as we return to the Moon with Artemis, as private lunar mission land, as satellites orbit the Moon, and eventually as permanent bases establish, LTC will be central. It turns the Moon into a world with its own heartbeat. Where once Earth time reigned everywhere, we now see that time itself shifts with gravity. On the moon, time runs a little faster. That speed, small though it is, demands respect. For humanity to live, work, explore, and survive beyond Earth, we will need a clock just for the moon. 500 days alone. Imagine being completely alone for more than a year. No day, no night, no phone calls, no clocks. That was the undertaking of Beatriz Flamini, Spanish extreme athlete, when she chose to live in a cave for 500 days to explore how time itself can slip away from us in isolation. Flamini entered the cave on November 21, 2021. She descended roughly 70 meters deep into a cave chamber near Granada, Spain. The chamber had high ceilings, but in that dark underworld, nothing outside penetrated. No sunlight, no sounds of civilization, no human presence. She would emerge again on April 14, 2023. Her project was called Time Cave. It was part personal discipline, part scientific experiment. She asked for minimal contact. She could send messages out but not receive them. A volunteer team provided supplies, removed waste, and monitored her via cameras and limited one-way communications, but inward, she was silent. Early on, she noticed disorientation in her sense of time. By day 65, she already lost track partly. She underestimated how long she had been underground. As months passed, her internal map of days and hours unraveled. Reports say she began to believe she'd been there for only 170 days instead of the full 500. In total, she read around 60 books over her stay, drew, knitted, exercised lightly, moved about her cave space. She brought a Harry Potter wand stick for symbolic support, 2 stuffed toys, though she refused to treat them as companions, clothes, food, supplies. She avoided habits that might anchor her to the outside, such as speaking to an imaginary friend. By video logs, in early days she attempted to organise her space, mark sectors, pace pathways. She would talk into her GoPro camera, narrating, self-reflecting. She disciplined herself. What shall we eat today? Beans or lentils? Exercise or rest? She tried to maintain a semblance of a routine, but that routine warped. As time passed, she sometimes spent 3 days without signalling bedtime to her team. She slowed, drifted. Vivified dreams, hallucinations, boundary between waking and sleeping blurred. Some days she barely left her tent wrapped in darkness. Her sense of memory, of sequence, of what came before, faltered. She complained to GoPro audio logs about the absence of time cues. "It's always 4 in the morning," she once said in confusion. She speculated on the growth of armpit hair as a time measure, but even that failed. Her internal metrics lost meaning. By about day 300, she left the cave briefly for 8 days to correct a technical issue with her Wi-Fi router. During that time, she stayed in a tent at the cave's exit, maintained silence and isolation. Then she descended again, determined to complete the 500 days. That episode raised questions about whether the intended continuous isolation record was fully preserved. During the whole period, scientists from the universities of Granada, Almeria, and Murcia collected data. Psychological assessments before and after, recordings, video logs, possible circadian rhythm measurements. They intended to study how extreme isolation, deprivation of external cues, and extended solitude affect human cognition, memory, time perception. When she finally emerged, Flamini said she could not believe how fast time had gone. She joked that she thought she'd been in the cave a few months, not nearly 1.5 years. She lost weight. Her balance and peripheral vision were impaired. Her pupils had trouble adjusting to light. Her short-term memory was degraded. Sudden noises startled her, because in the cave she had no peripheral awareness. Everything was direct, in front of her headlamp. She described how the darkness sapped her, not physically, but in the sense of identity, of continuity. She told reporters, "I did not have time to miss anyone." Time felt like a single night. Compression of long stretches into a mental instant. From her experience, we can glimpse how much of our time sense depends on cues. Sunrise and sunset, clocks, routines, shared schedules, social contact. In the cave, most of these vanish. The mind must reconstruct time internally, and over months that reconstruction begins to crumble. Cognitive scientists propose that time perception relies on memory encoding. We measure duration by how many changes, how many events, how many novel bits are stored. When each day is similar to the next in a featureless environment, fewer memory markers accumulate and the subjective length of time shrinks. In Flamini's reports, she said that after a while, days blurred, nights merged and novelty faded. Her mind had fewer landmarks to mark passing. When she emerged, she met reporters, lights, voices, and the contrast felt overwhelming. Her isolation parallels earlier cave experiments. Michel Siffre, Maurizio Montalbini, Stefania Follini, but her duration, volume of solitude and self-imposed restrictions pushed further. Some of those experiments also observed drift in sleep cycles, disorientation, shifts in circadian rhythm, memory lapses, mood changes. Flamini's experiment extends that literature into deeper timescales. Her expedition also prompts reflection on how humans keep time socially. Calendars, public institutions, shared timekeeping, clocks, daylight. Without those, our interior clocks struggle to stay aligned. For psychologists, her journey offers data points. How time, memory, identity, perception warp under prolonged sensory and social deprivation. How much of our self is anchored by external time, and how fragile our internal clock is when left on its own. For all she endured, Flamini emerged upbeat, joking, articulate, though she acknowledged post-traumatic stress signs in her recovery. But she insisted the experience was positive. I could have stayed longer. She said her interior conversations had grown friendlier, that she learned to tolerate silence, to carry herself. Her emergence also raised debates about whether her temporary exit broke the continuous isolation and whether the record counts. But for the purposes of time perception, her entire stretch remains instructive. 500 days underground teaches us about time unmoored. How long can we drift before the mind itself loses the mooring of hours, days, memory? At last, when she climbed out, she sang. She joked that she said to the cave, "Before we go, would you like something? You're in my home." She left behind her tent, drawings, her sleeping bag. And stepping into daylight, she rejoined the flow of shared time, a world she had not perceived for more than a year. BSAA Stardust and the word Stendek. In 1947, an airliner vanished into the Andes. For more than half a century, it lay buried in ice. Its last message, a single cryptic word, Stendek. That ghostly Morse code signal whispered through time until, in 1998, the glacier gave back fragments of the wreck and renewed debate over that final transmission. On August 2nd, 1947, British South American Airways BSAA Flight CS59, a Lancastrian named Stardust, registration GAGWH, left Buenos Aires bound for Santiago, Chile. The flight planned to cross the Andes at high altitude. The crew was experienced the weather acceptable, though clouds masked mountain peaks. During its final leg, Stardust radioed its estimated time of arrival, ETA Santiago 1745 HRS. Then came its final Morse code message, Stendek. Ground radio operators in Santiago heard the message loud and clear, though sent with unusual speed. Not recognizing the word, they asked for clarification. The airplane repeated it, Stendek, Stendek. After that, the line went dead. No more transmissions, no sign of the aircraft. A massive search followed across mountains and valleys, but no wreckage was found. Over decades, theories abounded. Some speculated sabotage, or a mid-air explosion. Others whispered of secret diplomatic cargo, stolen gold, or even alien abduction. Because Stendek had no obvious meaning, its enigma stoked rumours. Some thought it was an anagram of descent, a scrambled message about beginning descent. Others suggested misspaced Morse, poor encoding, or even a cipher, but no explanation ever gained acceptance. Then, in 1998, something changed. Two Argentine mountaineers trekking near Mount Tupungato stumbled on wreckage protruding from a glacial face. They found twisted metal, a Rolls-Royce engine block, fragments of fuselage, relics of the long-lost plane. The discovery prompted an Argentine army expedition in 2000, which recovered more parts: wheels, one still with an inflated tyre, a propeller, structural components, and even human remains preserved by ice. DNA tests helped identify some of the victims by 2002. Analysis of recovered fragments revealed crucial clues. The propeller showed signs that engines were running at cruise speed at impact. The landing gear was retracted, indicating the aircraft was not in a landing attempt but in full flight. The wreckage pattern suggested a high-speed direct collision, possibly into a snow slope. perhaps triggering a landslide or avalanche that buried the plain deeply in glacial ice. Operating at altitude near cloud cover, the crew may have misjudged their position. In the 1940s, jet streams were poorly understood. A strong headwind from high-altitude winds could have slowed the plane's ground speed unexpectedly, causing the crew to believe they had crossed the mountain range. Confident of clear terrain ahead, they began a descent, just as they were still above hidden peaks. The slope of Tupungato and dense cloud cover masked danger. The plane, descending under false assumption of location, struck a ridge or snowfield. Impact likely triggered a localized avalanche that buried the remains almost at once. The glacier gradually consumed the wreckage, embedding fragments in its flow. As the ice moved and melted, debris slowly emerged decades later. And so, after 50 years, the glacier gave back evidence. But the biggest mystery remained: Stendek. What did it mean? Radio experts weighed possibilities. Could it be a garbled descent? In Morse, Stendek and descent share many dot and dash sequences, and misspacing or mistiming of Morse signals can turn one into the other. But decoding Stendek as descent introduces problems. Repeated twice, it seems redundant. Also, descent would be expected in normal context. Why scramble it? Another theory. Stendek may have been an acronym. Perhaps start en route descent or severe turbulence encountered, need descent emergency crash. But no documented use of Stendek as phrase existed in aviation records, and no radio shorthand matches. Some speculated that the radio keyer slipped, or that the Morse spacing was chaotic under stress. The BBC Horizon programme, investigating the case, concluded that the simplest explanation may be misspacing or garbled Morse, but admitted none of the proposals are fully convincing. Some suggested the radio operator was suffering hypoxia at altitude. Maybe his brain scrambled characters, or that the fast speed of the Morse transmission compressed spaces, hiding correct decoding, or the ground receiver misheard or misinterpreted spacing. In Morse, spacing is as significant as the dots and dashes themselves. Even certain alternative decodings propose that Stendek is identical in Morse to SCTIR, the call sign of Santiago Airport plus AR equals sign over. With a shift in spacing, the message could be read as ETA Santiago 1745 SCTIAR, that is, expected time of arrival Santiago 1745 over. This theory implies the radio operator simply encoded call signs compressed, but that fails to explain why Stendek was repeated twice. Why repeat SCTIAR? Another hypothesis links Stendek to Valparaiso Airport call sign via off by one Morse shift. But these interpretations feel contrived, lacking confirmation or coherence with the crew's context. The recovered wreckage forced re-evaluation of the search area. Based on reveal sites, analysts projected how the glacier flowed, how debris emerged, and estimated probable crash elevation. Coordinates around 33°21s, 69°43, W heights between 4,400 and 4,700 meters came under focus. The debris field spans about 800 meters. As of early recovery, only about 10% of total expected wreckage has emerged. The official investigations in Argentina and the UK examined weather, flight logs, pilot experience, and radio transcripts. The British Ministry of Civil Aviation's 1948 accident report conceded that lack of wreckage prevented definitive conclusions. The Argentine investigation, after finding debris, cleared the crew of wrongdoing, attributing the crash to weather and misnavigation due to cloud cover and wind. Yet those reports don't resolve Stendek. Because the Transandean route was dangerous and radio communication limited in those days, landing decisions and descent timing depended heavily on navigation fixes and visibility. The crew, flying in clouds, may have executed descent based on erroneous position estimate. They might have believed they had cleared the Andes. That misassumption is consistent with engines running and landing gear retracted. Though technology has advanced, Stendek remains unexplained. Some aviation historians accept that misencoded Morse is the best explanation we have. Others argue for hidden codes or deliberate obfuscation. But no archival evidence supports a covert meaning. The case also exemplifies how time can hide accidents. For decades, the plane sat frozen, waiting centuries for fragments to emerge. Its story is marked by silence, by missing days, by signals sent into thin air with no answer until decades later. It fits our theme, the way time, ice, message, and gravity conspire to delay truth. In the cold, slow world of glaciers and Morse echoes, Stardust and Stendek remain a chilling whisper across years. The word repeats in archives, in speculation, in shadowed corridors of aviation lore. And when fragments surface from the ice, we chase evidence and interpretation, but Stendek endures as the last cryptic foot in the logbook of a vanished plane. Leap-second glitches. On June 30th, 2012, at 23:59, 60 UTC, the world's clocks gained an extra second. That leap second slipped into time quietly, but it unsettled systems everywhere. Some servers crashed, websites slowed, network systems glitched. What became known in tech circles as the Lepocalypse revealed how brittle our infrastructure can be when time changes in unexpected ways. Leap seconds are needed because Earth's rotation is not perfectly steady. Atomic clocks, which measure the second as a fixed number of oscillations, gradually drift ahead of solar time, which depends on Earth's spin. To realign them, systems called UTC sometimes insert an extra second at the end of a day. Since 1972, 27 positive leap seconds have been added. But that adjustment is rare and irregular. Software and systems, for the most part, do not expect a minute with 61 seconds. Many systems assume time always moves forward in a strict, steady sequence. 00, 01, 02, 59, then wrap to the next minute. A sudden 60 breaks that assumption. In 2012, when UTC inserted that extra second, many Linux servers experienced severe CPU usage spikes. The HR timer subsystem, responsible for high-resolution timing and waking-sleeping processes, misbehaved. Processes that should have waited or slept were instead woken en masse. The system overloaded itself. Sites and services across the web were affected. Reddit servers hung, making the site unavailable for tens of minutes. Mozilla, Gawker, Yelp, Foursquare, LinkedIn also saw disruptions. In some cases, servers logged 100% CPU usage. System schedulers became overwhelmed. Processes entered tight loops, and services effectively halted. In some Java-based systems, the sudden time inversion or non-increment broke APIs expecting consistent forward time. Some functions encountered negative time intervals, causing exceptions or unexpected behavior. Database services, task schedulers, logging systems all proved vulnerable. Airline reservation systems were not immune. The widely used Amadeus Altéa reservation system encountered hiccups. Qantas Airways reported that the leap second caused system slowdowns, affecting bookings and departures. In that moment, an invisible second forced disruptions in the physical world of travel. Administrators scrambled. Some patched their kernels, others rebooted servers. Some turned off NTP, Network Time Protocol services, letting internal clocks drift temporarily to recover. Others applied updates to fix the HR timer bug. Many issues went away after reboots. Programmers and kernel developers had known leap-second risks existed. But because they occur so rarely, much of the affected timekeeping code goes untested under those conditions. Linus Torvalds of Linux once said that leap-second bugs are classic. Code paths rarely run, so bugs hide for years until they trigger. After 2012, many server operators adopted one of two strategies to avoid future disruption: slewing, spreading the extra second gradually over a longer period, or smearing, a more aggressive gradual adjustment. Google, for instance, applies a leap smear, stretching that extra second across many hours so that system clocks never see a 23:59:60 event. Some systems bypass leap second insertion entirely by using TIE, International Atomic Time, or GPS time internally, converting to UTC only for human-readable timestamps. That isolates their internal logic from the unpredictable UTC shifts. Further leap seconds after 2012 also triggered minor disturbances. In 2015, cloud systems, routers, and DNS servers saw delayed responses or timestamp mismatches. Some older Cisco Nexus switches hung, and services like Twitter or Instagram had brief glitches. In data center operations, network time distribution becomes tricky. NTP servers must announce the upcoming leap second, but many client systems ignore or misinterpret that warning. Some misconfigure clients in which the leap second flag is mishandled, leading to time synchronization errors. The crux, when systems assume continuous monotonically increasing time, a sudden extra second breaks assumptions. It can cause loops, timeouts misfire, cache invalidation fail, scheduling misalign. In distributed systems, clocks must stay in sync. If one node thinks time jumped differently, coordination breaks. Even more subtle, some timestamping systems don't recognize leap second as valid input. A timestamp 2359. 60 may be out of expected range, causing errors or crashes in applications that pass time strings or convert between formats. In GPS and satellite timing systems, leap seconds are handled differently. GPS time does not include leap seconds and runs continuously. GPS receivers therefore maintain an offset between GPS time and UTC, updating when leap seconds occur. Some GPS receiver firmware mismanages that offset, leading to off by 1 second errors in positioning or data logging. As the world depends more on distributed systems, precise timing, financial trading, power grids, communication networks, and navigation, even a single leap second can propagate as chaos. Engineers discuss whether leap seconds should be phased out. In 2022, at the General Conference on Weights and Measures, a resolution was passed to abandon leap seconds by 2035, letting UTC drift gradually. Each leap second still scheduled ahead creates a maintenance risk. Each adjustment must cascade through operating systems, logs, hardware clocks, firmware, networks. The bigger our reliance on time-sensitive operations, the more fragile that one extra tick becomes. In tracing the 2012 leapocalypse, we see not a cosmic mystery but a systemic weak spot. A single extra second, one real physical second, entered into the walls of trillions of lines of code, in servers, routers, control rooms, and airline systems, and the systems wobbled. As we step into a future of greater time precision, the lesson is clear. Human timekeeping may bend for Earth's rotation, but our systems must be resilient when time itself bends. Each leap second is a test, and in 2012, many systems failed the test. Ancient seeds wake up. In the arid heat and shifting sands of Judea, a seed slept for 2 millennia. Encased in dryness, hidden in clay jars, it lay waiting through generations, through conquest and collapse, through silence and oblivion. Then one day, with water and light, it stirred, and life emerged again. This is the story of the ancient Judean date palm, resurrected from a 2000-year dormant seed. The Judean date palm, Phoenix dactylifera, was once a symbol of fertility and abundance in ancient Israel. It thrived along the Jordan Valley near the Dead Sea, in oasis groves fed by springs. In biblical texts and classical writings, the date palm is praised for sweetness, longevity, and its standing as a pillar of desert cultivation. Over centuries of climate change, conflict, and shifting agriculture, its presence waned. Many believed that the original Judean palms had vanished. In the 1960s, during archaeological excavations at Masada, the cliff fortress built by Herod, the remains of clay jars were found. In some jars lay date seeds preserved in dry conditions, sealed away. Radiocarbon dating later determined that these seeds dated from between 155 BC and 64 CE. The date pits had survived almost like time capsules in the dry Judean desert. Decades passed, the seeds sat in storage, held at Bar Ilan University and other institutions. Scholars wondered whether they were viable. In 2005, botanist Dr. Sarah Salon proposed attempting to germinate some of those ancient seeds. She asked Dr. Elaine Soloway at the Arav Institute's Center for Sustainable Agriculture to take on the challenge. The odds were long, seeds typically lose viability over centuries. But the Judean climate, the storage environment, and the robustness of date seeds gave hope. Soloway and her team began carefully. They hydrated the ancient seeds slowly, using warm water baths and growth hormone treatments in dilute fertilizer solutions. After weeks of patience and calibration, one seed sprouted. The shoot, a fragile green finger, emerged. That seed became the first resurrected Judean date palm, nicknamed Methuselah, in reference to the biblical patriarch famed for age. Time seemed to slip backward. Methuselah grew in a greenhouse in the Israeli desert. By 2008 it had several fronds reaching about 1.4 meters in height. In 2011 it flowered. Though as a male tree it produced pollen, not fruit. By 2015 Methuselah stood at around 3 meters tall, healthy and stable. That success encouraged others. The project attempted further germination. From a batch of 32 ancient seeds, 6 seedlings survived beyond early stages. Those seedlings were named Adam, Jonah, Hannah, Boaz, Uriel, and Judith, drawn from Judean and biblical themes. Genetic analysis of those trees showed they carry unique alleles and ancient gene diversity, offering insight into date cultivation in antiquity and the movement of date palm genetics across the Middle East and North Africa. In 2020, the trees bore fruit for the first time. Hannah, a female tree, produced dates pollinated with Methuselah's pollen. The first harvest yielded hundreds of dates, the product of a seed buried 2,000 years ago. The new fruit are being studied for taste, sugar composition, heritage traits, and comparison with ancient reports of Judean dates. This resurrection is not just botanical poetry, it's living history. The ancient seeds had effectively paused time. Their biological machinery survived inert through centuries, awaiting conditions to resume growth. In molecular and genomic terms, the seeds retained viability. Some dormant cells remained uncorrupted. DNA, minimal metabolism, protective structures like seed coats kept degradation low enough to allow life to resume. Researchers sequenced the genomes of these resurrected palms. The ancient date palms seem to show genetic affinity to both Middle Eastern and North African date lineages, suggesting that Judean cultivation once spanned trade routes and hybrid networks. The resurrected palms may contain alleles lost in modern cultivars, possibly contributing to climate resilience or disease resistance. In biological time, these seeds show that life can outwait centuries. In deleterious environments, dormancy is survival. For species with orthodox seeds, those that tolerate drying and dormancy, ancient revival is possible under near-ideal conditions. The Judean date palm is currently the oldest confirmed germinated seed of a tree species, pushing the limits of what we thought life could preserve. The name Methuselah is appropriate. Like him, the seed showed enduring age. Now the tree stands not only as a botanical marvel, but as a living link between antiquity and the present. When it flowers and fruits, it echoes agrarian gardens lost beneath the sands and history. In this story, place is protagonist. The scorched soil of Judea held seeds of its own past. The jars in Masada, the desert air, the arid heat, they formed a quiet archive. The seeds were dormant guardians of memory, waiting for a gardener to wake them. And when revived, they rooted themselves in the same land that once nurtured their ancestors. Standing beside Methuselah now, you might feel time's doubleness, the years it has lived, and the centuries it survived unseen. You might imagine the palms of Herod's day, the traders passing dates, the palms in oasis groves shading caravans. Those palms may have died, but their legacy waited in amber silence of seed. When modern scientists pollinate Methuselah with ancient pollen, or cross with other seedlings, they resurrect not just trees, but lines of heritage. Each branch, each date, is a connection between epochs. The trees grow new roots, but ancient roots run deep. The saga of these palms reframes our sense of time. We often view time as forward only, but biology shows it can pause, it can wait. A seed embedded in desert crypts can survive until human hands and favourable conditions revive it. The Judean palm teaches us that life can endure through time warp. In the desert twilight, where the sun sets behind the Judean hills, the palms whisper across millennia. A seed buried before Christ now pushes green leaves toward the sky. Time becomes circular. The ancient returns in new form. The past and present overlap in frond and date. The soil remains, the seed waits, and life awakens again. Tardigrades on ice. In 2014, a frozen moss sample from Antarctica gave up a secret. Under its ice, 2 microscopic creatures called tardigrades, also known as water bears, lay dormant for over 30 years. When researchers rehydrated them, one stirred, stretched, drank, and eventually reproduced. In effect, time stood still for these tiny animals. The moss had been collected in November 1983 and stored at 20 degrees Celsius. In May 2014, scientists slowly thawed the sample, soaked it in water, and examined it under microscopes. From the thawed moss, they isolated 2 adult tardigrades and 1 egg. The species was Acutuncus antarcticus, a hardy Antarctic tardigrade known for its resilience. On the first day after rehydration, one of the adults twitched a leg, a shy signal of life returning. Over days, movement increased. By day 6, the revived tardigrade was crawling and feeding. It resumed regular function. The egg also hatched, producing a juvenile that grew and behaved normally. But the real shock came later. The revived adult laid eggs, some 19 of them, and 14 hatched. The offspring also reproduced normally. The egg-derived juvenile likewise laid eggs, and its progeny hatched. In short, revival, recovery, and full reproduction after decades of suspended animation. However, the revival was slow. The revived organisms took longer to return fully to function than normal tardigrades. The first egg to hatch took 19 days, almost double the expected median of about 9.5 days. That lag suggests accumulated damage during the 30-plus years of cryptobiosis. In scientific terms, tardigrades can enter a state called cryptobiosis, where their metabolism drops to nearly undetectable levels. In this state, they can withstand freezing, dehydration, radiation, vacuum, and more. Their cells stabilize, often via protective molecules, and essentially pause life's processes. For most animals, decades of freezing or dehydration would kill cells by ice crystal damage, membrane rupture, DNA breakage, or oxidative harm. But tardigrades have evolved mechanisms to protect cellular components. Among these are special proteins and DNA repair systems. These let them endure the stress and emerge later. In this particular experiment, the ability to recover from organ damage, mend DNA, and restart metabolism was unexpectedly robust. Yet the slower behavior post-revival suggests those repairs were costly and gradual. The tardigrade's resurrection was a careful, incremental awakening. One revived adult, identified as SB1, eventually died about 20 days after rehydration, after laying eggs. The egg-derived individual, known as SB3, and its descendants, however, survived and reproduced. The second adult never fully regained full viability. These differences hint at subtle deterioration from long dormancy. Subsequent studies looked at the first-generation offspring of both SB1 and SB3, comparing their reproductive performance to that of typical, never-frozen individuals. The offspring showed no obvious abnormalities, suggesting that the damage didn't heavily echo into their descendants. The experiments mark the longest confirmed survival and revival period for tardigrades and their eggs under frozen storage. Previously, the record for revived frozen tardigrades was 8 years. For eggs stored dry, 9 years. This Antarctic sample shattered those records. This case is a vivid illustration of how life can pause itself. In effect, for those tardigrades, time outside, the decades passing in freezers and laboratories, did not register internally. Their cells waited, their metabolism suspended, their biological processes frozen in stasis. From the standpoint of our documentary, this is a natural time warp. It's not relativity or physics, it's biology pausing itself, hibernating across decades. In the frozen moss, time became a container, not a flow. For that small creature, time's arrow halted. When you watch a revived tardigrade stretch a leg, crawl, feed, lay eggs, you witness emergence from suspended time. You see the boundary between life and dormancy tipped, a being revived across human generations. In the broader picture, tardigrades fuel debates over life's persistence in extreme environments, in frozen worlds, perhaps even on comets or other planets. If a tiny animal can survive decades of frozen stasis and recover, what might live or wait elsewhere? The place, Antarctic moss, kept frozen in darkness, becomes protagonist. It held those tiny creatures in time's grip. The cold, the ice, the stasis, all protected, all preserved. Then in thawing, the place released them back into motion. Picture that moss, frozen in Antarctica, dark and cold, undisturbed for decades. In its layers, dormant creatures huddle, waiting. No heartbeat, no growth, no movement. Time's hand seemed paused there. Then human hands bring warmth, water, light, and life resumes. It is not just a creature surviving cold. It is a living link across generations, across decades. Biological sleep that outlasts human timekeeping. When we revive it, we are crossing temporal boundaries. When you think of time warp mysteries, ghost trains, echoes in space, clocks on stairs, the water bear in moss shows another. A biological time warp. Time paused, life preserved, reactivated. The microcosm that survived decades, waiting for us to listen, then live again. Oklo, the 2 billion year reactor that still keeps time. Deep in Gabon, in the Franceville Basin, lies a relic of Earth's deep past, a place where fission once burned naturally, uncontrolled by human hands. This site, known as Oklo, hosts natural nuclear reactors that operated about 1.7 to 2.0 billion years ago. Those reactors still carry the echoes of time and serve as a clock for fundamental physics. Oklo is not a man-made facility. It is a uranium ore deposit that, under the right conditions, became self-sustaining. In 1972, scientists analysing uranium from Gabon noticed something odd. The isotope uranium-235, required for nuclear fission, was depleted, more so than expected from natural decay. The anomaly could not be explained by standard geological processes alone. Additional study of fission product isotopes, neodymium, samarium, xenon, revealed that parts of the ore had once hosted sustained fission reactions. At the time those reactors operated, natural uranium had a higher proportion of 235U, perhaps 3%, compared to the 0.7% typical today. That made natural chain reactions possible under specific conditions. In the Oklo deposits, groundwater acted as a moderator, slowing fast neutrons so they could split more uranium nuclei. The geometry, chemistry, porosity and groundwater presence combined to create the rare circumstances for a natural reactor. Over hundreds of thousands of years, Oklo's reactors cycled on and off. Heat from fission boiled away water, shutting down moderation and stalling the reaction. Then the water returned, the reaction restarted. Studies modelling these cycles suggest on cycles of about 30 minutes active, followed by approximately 2 to 3 hours cooling, repeating over millennia. The power was modest, estimates are under 100 kilowatts thermal, but over geologic time the reaction consumed significant uranium and produced fission products trapped in the rock. Those products and isotope ratios remain as fossil markers. By analysing them, scientists reconstruct the reactor's operation, duration, and energetics. One compelling aspect: the xenon isotopes produced by fission were trapped in mineral crystals. The distribution of xenon isotopes corresponds with how quickly or slowly isotopic parents decayed, or how reactions cycled. Because the reactor turned on and off, the xenon record preserved the pattern. That gives insight into how the reactor ran over millions of years. Now, why is Oklo a timekeeper? Because this natural reactor gives us a window into fundamental physics billions of years ago. In particular, scientists use Oklo to test whether physical constants, like the fine structure constant, alpha, or nuclear cross-sections, have changed over time. If the rates of nuclear reactions were different then, the fission product ratios would show discrepancy. Researchers compare the neutron capture cross-section of the isotope samarium-149 from Oklo samples with modern laboratory values. That capture resonance is sensitive to alpha. If alpha had changed, the resonance energy would shift, changing how many neutrons samarium absorbed in reactions. Because we see that samarium in Oklo behaves nearly identically to present values, we conclude that alpha has changed by at most parts per 10 circumflex 7 over 2 billion years. Other studies place constraints on the strong nuclear force or proton-neutron masses coupling or other coupling constants. Oklo's record is one of the tightest bounds we have on whether forces, charges, or quantum energies vary over deep time. In that sense, Oklo itself is a protagonist, a reactor site, a rock lunette, a geologic system that keeps time not by ticking but by preserving isotopes, reactions, and constraints on physics. It is a fossil reactor clock. The uranium ore, the groundwater veins, the mineral matrix, all contributed to the reactor's operation and preservation. The strata above preserved the reaction products, geologic stability, limited migration of isotopes, minimal disturbance. These are what allowed the record to survive through eons of tectonics, heat, erosion. In order to analyse these constraints, scientists perform neutronics modelling of the reactor cores, reconstructing core geometry, neutron flux, moderator content, temperatures, fluid flow, isotope diffusion over time. Modern simulations use Monte Carlo codes to match observed isotopic distributions to plausible reactor histories. They must account for uncertainties: how hot the reactor was, how water moved, how impurities or poisons like xenon altered operation. Even small changes in temperature or water content would shift the reaction balance and isotope yield. Their models need to be robust, from isotopes like ruthenium, neodymium, plutonium traces, technetium, and so on. Geochemists reconstruct fission yields, durations, and how far isotopes migrated. Many non-volatile products remain within centimeters of their original positions, revealing that the system was surprisingly stable over billions of years. But that stability is also what lets Oklo constrain physics. If something fundamental changed, part of the reactor record would diverge. The match to present physics is remarkable. Over 2 billion years, nothing obviously shifted. When you stand on the rock near Oklo, imagine water percolating, uranium atoms splitting, neutrons dancing, heat boiling away water, stopping reactions, restarting. Reaction cycles tuning themselves via geological feedback, and then time, with its constants, echoing through to our analytical wells today. In one sense, Oklo is a geologic clock more precise than a man-made atomic device stretched over eons. It measures not seconds, but the consistency of nature's forces over deep time. So in this chapter, place becomes character. The uranium veins, groundwater channels, mineral matrix, rock strata, all collaborate. The reactor zones at Oklo speak across billions of years. Their isotopic record is a slow pulse, a whisper of nuclear time. When we mine uranium from Oklo today, we are touching a site that once burned itself, moderated by water, controlled by nature. We are handling material once part of a reactor cycle. Every isotope ratio is a page in a logbook written billions of years ago. Time in Oklo is fossil, time is constrained, time is preserved. The reactor that burned itself into memory continues to tell us not just how Earth worked in the deep past, but whether the laws of nature have remained stable. This is a reactor that still keeps time, not by seconds, but by nuclear chronometry embedded in rock. The neutrino that wasn't faster than light. In September 2011, the physics world braced itself. The Opera experiment at Gran Sasso announced a result that seemed to break the universe. Neutrinos travelling faster than light. The data claimed neutrinos from CERN in Geneva had arrived at Gran Sasso 60 nanoseconds earlier than light, would over the same 730 kilometers path. The claim challenged a pillar of modern physics. The Opera collaboration was measuring the time of flight of neutrinos. They knew the starting time when neutrinos were produced at CERN and the arrival time when detected at Gran Sasso. They used high-precision GPS, atomic clocks and careful calibration to match those times. Anything arriving earlier than expected, faster than a CC, would be extraordinary. Initially, the data showed neutrinos arriving about 60.7 nanoseconds ahead of light's predicted time. The measurement was repeated using higher energy neutrinos. The result held. Neutrinos appeared to beat light by 1 part in 42,000. The team cautioned that this was an anomaly, not a confirmed discovery. They invited scrutiny. As the news spread, many physicists reacted skeptically. Einstein's theory of special relativity has withstood countless tests. If neutrinos could travel faster than light, the implications would shake the foundations of physics. But the odds favoured a subtle error. In early 2012, Opera announced 2 probable sources of error. First, a loose fibre optic cable linking the GPS signal to the Opera master clock. That loose connection delayed the timing signal by tens of nanoseconds, essentially causing the neutrino's arrival time to look earlier than it should. The fibre link had underestimated the delay, making neutrinos appear faster. Second, a clock oscillator on an electronic board ran slightly faster than its 10 MHz standard, introducing a drift of up to 74 nanoseconds over a 0.6 second data chunk. Because the master clock drifted, timestamps inside each chunk could shift, further skewing the measurement. To verify, the Opera team collaborated with engineers and experts. They found photographs showing that the fibre optic connector was not fully screwed in, consistent with the looseness causing delay. They compared timing with another nearby experiment, LVD, using cosmic ray muons passing through both detectors. That cross-check revealed a shift of about 73 nanoseconds matching the observed neutrino anomaly during the period when the fibre was loose. When the cable was tightened and the clock behaviour corrected, the apparent early arrival disappeared. New measurements, corrected for the error sources, showed neutrino speeds consistent with the speed of light. In July 2012, Opera published updated results that no longer claimed superluminal neutrinos, Independent experiments had already challenged the superluminal claim. The Icarus experiment, operating in the same lab complex, measured neutrino velocities in the same beam and found them consistent with light speed, contradicting Opera's initial claim. What made this episode unusual is how public the reversal was. Typically in experimental physics, errors are quietly found before publication. But Opera's result was public, sensational, and its correction just as open. It became a case study in scientific method, error correction, and the pursuit of truth. This chapter blends myth and archive. The myth is the headline: Neutrinos outrunning light. The archive is the full log, the calibration files, the photographs of connectors, the clock corrections, the cross-checks, the public retractions. The story is not that neutrinos beat light, but that science beat an error. Opera's instruments had many complexities: long fiber links, GPS-based synchronization, cascades of electronics, signal chains that stretched kilometers underground. Each link in that chain had to be calibrated precisely. A single misconnection or drift could ripple into a 60 nanosecond effect. In that stretch of time, nanoseconds compressed over long distance, we see how fragile our measurement chains are. The experiment showed how pushing to the edge of precision forces all the hardware, firmware, connectors, and analysis pipelines to be perfect. A loose cable, a misaligned connector, a drifting clock. Any small error becomes magnified. Even after corrections, Opera's reversal did not tarnish physics. Instead, it highlighted how verification, replication, and transparency are essential. It reminded scientists everywhere: sensational claims demand double, triple scrutiny. Today the consensus is clear: neutrinos do not exceed the speed of light. Opera's anomalous result is now regarded as a cautionary tale, a near miss in precision timing. Yet it remains a compelling time warp mystery. For a moment we thought the universe's speed limit had cracked, until human error closed the gap. Seeing the moon 1.3 seconds ago. When scientists shoot a laser beam at the moon, they don't expect it to vanish, they expect it to return. Because on the lunar surface lie retroreflectors, arrays of corner cube prisms left behind by the Apollo and Lunokhod missions, that bounce light right back to its source. The time it takes the laser pulse to traverse Earth, Moon, Earth is about 2.5 seconds on average. That means when you see the moon in your telescope, you're literally seeing it 1.3 seconds in the past. Since the first Apollo mission in 1969, researchers have used lunar laser ranging, LLR, to measure the distance between Earth stations and the reflectors on the moon with millimeter precision. Each pulse is timed to extreme precision. The round-trip time gives a direct measure of Earth-Moon distance. Because light moves at a fixed speed, time and distance become interchangeable. Consider this. You dispatch a laser pulse. It races into space, reaches the moon's retroreflector, bounces off, and returns. The full journey takes approximately 5 seconds. In that time, Earth has rotated, the moon has moved, and gravitational effects have curved space. All of these must be accounted for, but that 2.5 second echo is the heartbeat of the measurement. In effect, seeing the moon through that timing means we see it 1.3 seconds ago. Over decades, as observatories around the world fire pulses at Apollo 11, 14 and 15 reflector arrays and Soviet Lunokhod ones, tiny delays or shifts in those returns encode physical behavior: lunar orbit change, tidal interactions, relativistic effects, even internal structure of the moon. The reflectors make the moon into a time-sensitive mirror. The optical arrays are passive, no power, no electronics, no moving parts. Just glass corner cubes fixed to the lunar surface pointed toward Earth. When photons arrive, each corner cube sends the light right back to its source. Because thousands of pulses are sent and many photons are returned, scientists can average timing to achieve a sub-centimeter accuracy. In recent projects like Apollo, Apache Point Observatory Lunar Laser Ranging Operation, they push these measurements to millimeter precision. Their laser pulses last tens of picoseconds. Their timing systems capture returning photons with resolution of a few picoseconds. Because 1 millimeter of distance corresponds to about 6.7 picoseconds in round-trip time, the instrument's sensitivity is astounding. However, the retroreflector arrays have limitations. Because the moon doesn't hold one face perfectly toward Earth, libration shifts orientation slightly. The corner cubes in an array then sit at slightly different distances to Earth, adding time spread in returns. That spread must be statistically averaged or modelled. Also, over decades the reflectors degrade. Dust, thermal cycling, micrometeorite abrasion reduce reflectivity and signal strength. The Apollo reflectors now return weaker signals, especially at full moon phases, where thermal gradients hamper performance. But even degraded, they return signals. For a laser ranging station, getting even a single photon back per few seconds is a success. The pulse spreads over kilometers, only a few photons make it home. Still, that's enough, with multiple pulses, to build a precise distance profile. By measuring the Earth-Moon round-trip time with great precision over years, scientists detect subtle changes. For instance, the Moon is receding from Earth at about 3.8 centimeters per year. The tidal interaction between Earth's oceans and continents causes Earth's rotation to slow and transfers angular momentum to the Moon, pushing it outward. The laser ranging confirms this drift. More, LLR experiments test general relativity, the strong equivalence principle, and search for time variation in Newton's gravitational constant. The tiny delays measured must be corrected for relativity. Gravitational time dilation from Earth and Moon, Shapiro delay through gravitational wells, atmospheric refraction, station motion, Earth tides, plate tectonics. The photon's path is influenced by many small effects. The timing residuals constrain physics. In each exchange, when Earth says ping to the Moon, we hear pong after approximately 5 seconds. That echo is not just a mirror. It's a measurement of motion, gravity, deformation, rotation, and time itself. Because the Moon's orbit and orientation evolve, the timing records must include relativistic coordinate transformations. When the reflector returns photons, those photons carry the imprint of gravitational potentials travelled, velocity differences, and even the curvature of space. The model includes these effects so that residuals reveal tiny anomalies. When mission control transmits to astronauts, or hears them speak, time-of-flight delays, approximately 2.6s, are audible in Apollo tapes. Similarly, the laser time-of-flight echoes connect Earth and Moon in a conversation of light. The Moon is always responding, 1.3 seconds delayed. Thus, when we view the Moon, our vision is not live. It's deferred by light's transit. Every crater, ridge, shadow we see is as it was 1.3 seconds ago. Not much for human perception, but for precision missions, that delay matters. For future lunar navigation, orbiters, landers, satellites, understanding that light time delay is critical. Signals must be timed, clocks synchronized, altitude computed. The retroreflectors provide fixed landmarks in time and space. They anchor the lunar time structure to Earth time. When we deploy new reflectors or optical transponders in future missions, the same echo logic will help spacecraft align, localize, and coordinate. The Moon becomes a networked mirror, echoing time across space. Every laser ranging experiment is an exchange. Earth initiates, Moon responds. Each return pulse is a frame of time. Over decades, those frames accumulate into logs of motion, gravitation, and lunar dynamics. The Moon becomes a chronometer. Its returned echoes track both where it is and how time flows between us. And so, in every lunar image, every moment we gaze upward, we are watching sunlight that left the Moon long ago, and timing pulses that echo from its surface after 1.3 seconds. The Moon is both distant and nearly immediate, a neighbour whose light always carries delay, and whose reflectors speak time back to us in echoes. Every one of these stories shows the same truth. Time is not steady. It's alive. It stretches, pauses, and sometimes loses its place. From the smallest particle to the movement of planets, time leaves fingerprints everywhere. And we are still trying to read them.